Assalamualaikum and very good morning. Welcome to chapter 13. It's gas laws and kinetic theory. So in this chapter we'll have a few linear outcomes and a few subtopics. So for 13.1 we have ideal gas equation. So what we're going to do for this subtopic is to discuss the following graph of an ideal gas. So we are going to have PV graph. P stands for pressure, V is volume, and then VT graph, volume versus temperature graph at constant pressure. PT graph is for constant volume, so pressure versus T, temperature at constant volume. So this is only valid for ideal gas. So we'll see what is the meaning of ideal gas. And the second learning outcome is to solve problems related to ideal gas equation. So we're going to use PV equal to nRT. So I believe that you have used with this equation during your secondary school. Okay, so first we're going to start with Boyle's law. Okay, so Boyle's law states that for a fixed amount of mass of a gas at a constant temperature, the gas pressure will inversely proportional to the gas volume. So as we increase the pressure, the volume will be decreased, or as we increase the volume, the pressure will be decreased. So we can see the examples in here. So if we give more pressure to this piston, we call it piston, the molecules inside this volume will be moving not quite freely, so the pressure increase compared to this one. Okay, we are increasing the volume, so we can see here that the molecules inside are moving more freely. So this represents that the pressure is increased. So this is what Boyle's law is all about. Okay, so from this equation, P is inversely proportional to volume. So if we make up an equation, we bring P to the left. Sorry, we bring V to the left. So we are going to have PV equal to constant. So for a few conditions, like we have two conditions, we can always compare that P1 V1 is equal to P2 V2. Okay, so this equation is for Boyle's law. Okay, so this is the graph of Boyle's law. If we are going to plot the graph of pressure versus 1 over V, we're going to have straight line graph. And if we want to plot the graph of pressure against volume, it's going to be a quadratic, inversely proportional graph. Okay, it is decreasing exponentially. Okay, the next law is Charles' law. So Charles' law states that for a fixed amount mass of gas at a constant pressure, gas volume is directly proportional to its absolute temperature. Okay, so as we increase the temperature, logically we can think of the volume. Okay, when we increase the temperature, the volume inside here, the volume inside here will be moving freely, so they will start to push away the piston here, so the volume will be increasing. Okay, so increasing the temperature meaning you are increasing the volume. Okay, so we put it into constant. T, bring it to the left, so we're going to have V over T is equal to constant. So if we have a few conditions, we have V1 over T1 is equal to V2 over T2. And this is the graph of Charles' law. If we are plotting V against T, so we have straight line graph. And if you want to go plot of V against T, but now it is in degrees Celsius. As we know, 1 Kelvin is equal to you have to plus 273.15 815 to be in degrees Celsius. So the graph will start from negative 273.15 degrees Celsius. It's not going to start from 0. And the next law is Gay-Lussac law or pressure law. So for pressure law, for a fixed amount of gas at constant volume, gas pressure is directly proportional to its absolute temperature. So as we increase the temperature, the pressure must be increased. Okay, because when we increase the temperature, the molecules inside this region or this volume will move faster, will vibrate faster. So they will collide with the wall of this piston, of this cylinder, making the pressure increases. So if you could realize, all these volumes are the same, but if the temperature are different, the pressure will be also different. So moving this T to the left, so we're going to have P over T is equal to constant, and if we have a few conditions, P1 over T1 is equal to P2 over T2. And this is the graph from this equation. This is the graph of P against T. It is directly proportional. And again, if we start our temperature, if you want to plot our temperature in the unit of degrees Celsius, it's going to start from negative 273.15, because 1 Kelvin is equal to you have to plus 273.15 to get the degrees Celsius. And then we have ideal gas equation. Okay, so where is it coming from? So for this ideal gas equation, the three laws that we have learned just now is combined into a general law known as general ideal gas equation. So if you realize, previously all those three laws are talking about three quantities: pressure, volume, and temperature. So if you want to look at the how the quantity is changing, we'll see that one quantity is constant. Like for the Boyle's law, when we change the pressure, volume is changing, but then the temperature is constant. Okay, and then for the next laws, one of these quantities must be constant. So ideal gas equation is special because all these three quantities P, V, T are changing. Okay, and if you divide these three equations, PV over T is equal to constant. It is equal to constant. Okay, so if you can see here, P1 is changing, V1 is changing, T1 is changing, and this is the second condition, and this is the third condition. Okay, so just now, okay, we have this equation. PV is equal to PV over T is equal to this value, 8.31. So 8.31 is known as, okay, the molar gas constant R. Okay, and bear in your mind, this value of 8.31 is acquired from the substitution of value of P, V, and T at standard temperature and pressure. Okay, you can just Google what is the standard condition for STP. So it's T must be 0 degrees Celsius. This is equal to 273.15. Pressure must be 101.3 kilopascal. Volume must be 22.4 decimeters cube. So substituting all these values, we'll have PV over T is 8.31 for 1 mole of gases. Okay, I believe you have learned about this the term mole or molecules in chemistry subject, isn't it? Okay, so if we have the equation, if we have 1 mole, okay, so the equation 8.31 here is known as molar gas constant. So PV over T is equal to R, or PV over T is equal to 8.31. Okay, but bear in your mind this is only for 1 mole. So if you have more than 1 mole, we have to add up one more term, that is small n here. So the equation becomes PV equal to nRT. So n here means the number of mole. Okay, so if you have 2 moles, we have to substitute 2 here. So the general equation is equal to PV equal to nRT. So this is what we call ideal gas equation. So why we mention ideal? Why we are learning about ideal, or why the word is ideal? Because the gas that we are learning now, we assume that they are ideal. So we're gonna look in later in the content that ideal means all the gas molecules are having the same volume and a few more conditions. Okay. In reality, all the gas molecules are not ideal. But then to put it into theory, we have to assume that all the gas molecules are ideal. Okay, ideal means perfect. Okay, so we have PV equal to nRT, but you have to know that this equation can also be expressed in this expression. So instead of having nR, we can also write down this equation as PV equal to nKT. So here is small n, but here is big N. Okay, big N is the number of molecules, small n is number of moles, so they are different things. So how to relate these two equations is that we have to know this relation. K, Boltzmann constant, is equal to molar gas constant R over Na, Avogadro number. That is 6.03 times 10 to 23 molecules. So it's number of molecules in 1 mole. So you just substitute nRT with nK, R equal to KNA, so you get NKNAT. So knowing that N times Na, it is equal to N. Okay, we're going to have one equation here. So it's coming from this equation. Okay, it's coming from this equation. So number of mole is equal to number of molecules divided by number of Avogadro number. So number of molecules is equal to number of mole times Avogadro number. So that's why you put it here like this. Number of mole times Avogadro number will have number of molecules. So remember, n, small n, Na, and N are 3 different things. Na is not equal to N. Na is different, and small n is different, big N is different. Okay, you have to be careful with that. So ideal gas equations, so bear in your mind we have 2 ideal gas equations. It is depending, it's either you want to use N, R, or NK. Okay, so small n is number of moles, N is number of molecules. Okay, so that's all for chapter subtopic 13.1.